And welcome to calculus class. Here's what we're going to be doing. We're going to be taking a look at the derivatives of trigonometric functions. And so one of the first derivatives of trigonometric functions, well, I guess the main one that I can think of is the sine function. So let's say that we have f of x equals to sine of x. And we know what the graph of that looks like. It kind of looks like this. It starts at 0 here, and then it goes up to, well, we know it goes down to 0 again at pi, and over right exactly halfway there at pi over 2, it goes up to 1. And so, and then over here at, let's see, 2 pi, it goes back to 0, and so that would make this part 3 pi over 2, or 1.5 times there. It goes down to -1. And we know that the graph looks very smooth, so it kind of looks like this. Oh, ooh. Doesn't look like that, huh? Looks kind of like that. Nice curvy action going on there. There we go. And it continues on forever and ever that way too. And like that. Cool. All right. So if we were to balance a bar or a tangent line over here, this part right here would be a horizontal point. In fact, all of the peaks of the sine function and the troughs of the sine function will have horizontal. That's where it touches the horizontal. So let me just draw another graph underneath, and this one's going to be a little bit different. This one is going to say, all right, if this is f of x equals sine of x, then I want to graph f prime of x. And what is that equal to? Okay, so over here, let me just put my points in here again. Notice how I'm aligning these points to correspond with the graph on top. That way you can kind of see exactly how these things align. Alright, I just told you that this point right here is horizontal, so then the slope of it is 0. And over here is horizontal, so the slope of that is 0. Now, at this point right here, this looks like is where it's going up the most. And so I'm going to set that equal to 1 or something high up there. And then as it comes over here, it gradually gets smaller and smaller until it gets to 0. So something like this maybe. All right, now over here, definitely at pi, the graph is equal to negative maximum. And then over here, it goes back to equaling 1. So something like that. And again, all of these transitions are really smooth. So something like this. Oh, wait, what happened? Maybe? And if you know what your trig functions are, you can tell me, hey, wait a second, that's the graph of cosine of x. And the answer to that is it absolutely 100%ly is. The derivative of sine of x is the cosine of x. In fact, let me just kind of recap for you all of the derivatives of the trig functions. I guess I'll prove one to you. There's a much more sophisticated and complicated proof, and I could spend maybe 15 minutes explaining that to you, but I want to get into some example problems. So I'm going to skip actually doing the complicated proof of sine of x and just say, hey, look at my hand wavy proof, and hopefully that will convince you that that's the case, and then we'll see what happens there. All right, so to recap, let's see. I know that the derivative with respect to x of sine of x is equal to the cosine of x. I know that or at least similarly, I could prove that the derivative of cosine of x is not equal to sine of x. It's equal to negative sine of x. Trust me, remember that negative. It gets me every time when I'm proving things. The derivative of tangent of x is equal to the secant squared of x. And you've got these kind of obscure ones, but it's worth noting, so I'm going to write them down. ddx of the cosecant of x is equal to negative cosecant of x times the cotangent of x. The derivative of secant of x is equal to secant of x tangent of x. And the derivative of cotangent x is equal to negative cosecant squared of x. And I told you, I promised you I would prove to you one of them. I think what I'm going to do is I'm going to prove to you the tangent one, because I think that's a pretty important one. Alright, so let me show you that the derivative of tangent of x, well, let's just figure out what it is. First, we know that the derivative of, well, we know what tangent of x is. Tangent of x is actually sine of x divided by the cosine of x. Now, some of you like to use the product rule, and that's fine. Actually, you know what? I wanted to show you a different technique of using the product rule, but I can't do that until I teach you the chain rule, which I'm going to do at some point today too. So let's just use the product rule for now. All right, the product rule says, what was it? It was low d high minus high d low all over low low. What I mean by that is, see the cosine of x, that's low, and the sine of x, that's high. So you have the cosine of x times the derivative of sine of x minus the sine of x times the derivative of the cosine of x all over cosine of x squared. And we usually write that like that. Alright, well, we know what this is. The derivative of sine of x is cosine of x. So this would be cosine of x times the cosine of x, also known as cosine squared of x. And this is sine of x times the negative sine of x, because the derivative of cosine of x is negative sine of x. So I guess this would change into a plus, right? Over cosine squared of x. All right, and then we have, let's see, cosine squared of x minus, or no, plus sine squared of x all over cosine squared of x. And by the Pythagorean identity, cosine squared plus sine squared, or maybe you might know it as sine squared plus cosine squared, is equal to 1. So I have 1 over cosine squared of x. We know that 1 over cosine of x is defined as the secant of x. So I'm actually, since I have cosine squared, I actually have secant squared of x. And voila, QED, tangent of x is, or the derivative of tangent of x is equal to secant squared of x. Cool. All right, let's hang out on this video, and then I will show you a bunch of example problems. Let's get into it.